Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
All right, good afternoon. We're delighted to have Liang Tan tell us about depth hierarchy theorem for Boolean circuits.
Thanks, Yuval. Yeah, thanks for the opportunity to be here. I'm going to speak about joint work with Ben Rossman and Rocco Servedio. Ben's at Simons and Rocco's at Columbia. So this is a talk about circuit complexity. So very briefly, let's recall the broad goal is to derive strong lower bounds on the size of circuits computing an explicit function. So let me elaborate on two important words here. The first is explicit. For this talk, it's not very important. Let's think of an informal definition as concrete, simple to describe functions. So a non-example would be a random function. And I guess formally in complexity theory, we think of an explicit function as one being an NP. And as for circuits, the holy grail is really to understand the power of polynomial size n or naught circuits. The standard basis, or it's known as p/poly, which is not important. But so we'll ideally like to exhibit a function, a concrete, simple to describe function that cannot be computed by such circuits, which will separate p from np, but we're still very far from it. So the focus of research so far, and the focus of this talk is on restricted subclasses of p/poly. And in this talk, we will focus on one specific restricted subclass. So what's this class? It's the class of small depth Boolean circuits. So this is a Boolean circuit over the standard basis of n or NOT gates. We can assume, it's not hard to see that all the NOT gates are pushed down to the bottom, although this, again, not important for this talk. So that's the circuit, and we're interested in function that requires complex circuits. And so what's complex, there are two measures I'm interested in. One is depth, which is the number of layers you have. The other is number of size, which is the number of gates you have. Just these two. And we're going to make it even simpler and fix one of them. For this talk, we'll think of depth as a constant, say 100. And the only parameter we care about is the number of gates, which is size. And we are interested in very strong lower bounds on size, exponential. Okay, under this assumption that the depth is constant. Okay, so that's our model. Small depth circuits has been studied since the 80s, and it's really a story of success. Even since the 80s, we have exponential lower bounds against constant depth circuits computing an explicit function. So the landmark result here is that of Hastad, which we'll talk a lot about in this talk, and it builds on the work of Aitai, first Sipser, and Yao all in the 80s. And just as an aside, I should mention that it's quite rare in circuit complexity or complexity theory that we have such strong lower bounds. It's really among our strongest unconditional lower bounds in all of complexity theory. Okay, so that's, and the techniques that were developed to prove these lower bounds, they're important beyond circuit complexity. They're found in applications in pseudo-randomness, learning theory, proof complexity, and so on. And at a very, very high level, in this talk, I'm going to speak about an extension of Hastad's theorem, and we do so via a generalization of his techniques. So we hear a lot about Hastad's theorem, his techniques, and how we extend both of them. Okay, so let me go into detail about how long of this talk. I'm going to tell you about Hastad's theorem, and two of the extensions, neither of which are due to us, both due to him back in the 80s. One is average case hardness, and the other is a depth hierarchy theorem. I'll explain what each of these means in a second. You can probably guess what the first means already. And our main result is that we achieve both extensions of Hastad's theorem simultaneously. So as the title suggests, we prove an average case depth hierarchy theorem, which again, I'll try to explain what that means. After telling you about our main result, I'll give two applications, one in structural two fairly different areas, one in structural complexity showing that the polynomial hierarchy is infinite relative to a random oracle. I'll explain what that means. And the second, in a completely different area in the Fourier analysis of Boolean functions, we answer a question that's been floating around in the past few years about a converse to the famous Linial Mansour Nisan theorem, which I'll tell you about also. And if I have time, I hope they have time, I'll tell you about a technique, which is that of random projections, which is a generalization of Hastad's technique, which is random restrictions. So I'll tell you about random restrictions and what random projections are. Okay, so let's get started with Hastad's theorem. So Hastad's theorem, he proved exponential lower bounds against a constant depth circuits computing an explicit function. And the function is very explicit, the parity of x1 to xn. It really doesn't there's no arguing that this is explicit. It's concrete, it's simple to describe. Okay, so what does his theorem say? His theorem, in his PhD thesis, he showed that for every depth d greater than 2, think of d as 100. Any depth d circuit computing the n variable parity function requires size 2 to the n to the 1 over d minus 1. So in particular, if you ask me to build a depth 100 circuit and make me compute parity, I need lots and lots of gates, 2 to the n to the 0.01. So these are results we like in circuit complexity. It's a very strong lower bound against a very explicit function.
Is this tight?
Yeah, it's tight for parity. And in particular, beating this bound for a function other than parity is a big open problem. Yeah. So this is our best lower bounds against depth D circuits. Okay, so that's Hastad's theorem. Parity requires huge circuits.
The fan-in and fan-out can be
Unbounded, right. Sorry, I should have said that. Unbounded fan-in, but constant depth. Yeah, if it's bounded, then you cannot do much in constant depth. Yeah, sorry. Thanks for that. Okay, so this is Hastad's theorem. Simple. Let's talk about two extensions, both due to him. Okay, the first is average case hardness. So in fact, he proved something stronger. 2 slides ago, I showed that constant depth circuits of what seems like large size cannot compute parity. In fact, he shows in his thesis that depth D circuits of the same size, 2 to the n to the 1 over d, agree with parity only on a half plus little of 1 fraction of inputs. And in fact, the little one is very strong, exponentially small fraction of inputs. So this is hopefully clearly an extension. 2 slides ago, I said that such circuits cannot compute parity. This gives me more information. It says that such circuits cannot even correlate with parity. Okay? So just a few notes. Just the constant 1 function, a trivial depth 0 circuit, has agreement 1/2 with parity. So this sort of says that if you allow me to build a depth 100 circuit, you allow me size 2 to the n to the 0.01, which seems like a lot, I cannot do much better than a constant. If I'm lazy, I may as well just output a constant. I cannot even do an exponentially small fraction better than constant. So it's a very strong statement. And this is not too relevant for the talk, but as an interesting aside, this was implicit in his thesis, but the exact relationship between D and the size and the correlation bound was only recently pinned down by Impaglaso et al. And Hastad himself 30 years later. Okay, so this is the first extension, correlation bounds against parity. Let me talk about the second extension, which is that of a depth hierarchy theorem. And this will take slightly more time. In particular, I need some notation. AC0 sub D is a set of all depth D poly-n size circuits, or functions computable by them. So depth 2 is not very interesting. It's a set of all polynomial size, ors of n's or n's of ors, also known as CNFs or DNFs. Depth 3 circuits, depth 4, and you take the union of it all, you get AC0, which is the class of all functions computable by constant depth poly-n size circuits. In particular, parity is not one such function. Okay, so this is a cartoon picture of Hastad's theorem. It says that you have AC0, which is all constant depth circuits. And parity doesn't live in this green circle. In fact, if you want to compute parity with a poly-size circuit, you need depth roughly log n. So in a cartoon, it says that parity lives outside this circle at depth log n. So here's a challenge. I want the same lower bound against depth D circuits. So Hastad's theorem tells us that if you make me compute parity with depth D, I need 2 to the n to the 1 over d. So here's the challenge. I want the same lower bound against depth D circuits, but for a function that lives in AC0 depth D plus 1. Okay, so intuitively, this feels like a more challenging task. You want the same lower bound against the same class of functions, but for a much simpler target function. Right? In particular, you want it to be so simple that even just allowing me 1 layer more of depth, I can compute it in polynomial size. So this is hopefully also obviously an extension of Hastad's theorem. So, and then Hastad was able to do it. It's the so-called depth hierarchy theorem. And also in his PhD thesis, he showed that for every depth D greater than 2, there's a function fd, the so-called Sipser function, which I'll tell you about, such that fd is actually quite simple. It's in depth linear size depth D plus 1. But if you force me to use a depth D circuit, I will require an exponential blow up, 2 to the n to the 1 over d. And this is, again, just to recall the same lower bound we have against parity. Okay. So a few notes. It builds on the work of Sipser, and hence the Sipser function, which gave a super polynomial separation. And Yao, a few years later, gave an exponential separation, and it was sharpened by Hastad. Okay, and before Yao's work, the monotone case was solved by Kalai et al. It's the same theorem, just put monotone everywhere. There's monotone function fd. Sipser is monotone. Fd is in AC0 depth D plus 1, but the lower one only holds against monotone circuits. So it's a, yeah. And the hard function for all of the above is a Sipser function, which I'll tell you about. But before telling you about that, just very briefly, the conceptual message here is that, why is it called a depth hierarchy theorem? Is that, it says that depth D plus 1 circuits are much more powerful than depth D. You give me a nice linear size depth D plus 1 circuit, you make me decrease the depth by 1, I may have to blow up the size exponentially. Okay, so what's the depth D Sipser function? The formal definition is the depth D read once regular alternating monotone formula, but it's really the picture just says it all. You have alternating layers of n or, depth D. The fan-in is regular, it's n to the 1 over d. And it's read once, it's alternating n or. It's read once in that, the bottom layer and gates or OR gates touch distinct set of variables. And it's monotone, there are no NOT gates. Right, it's sort of the obvious depth D formula. It's sort of, if you made me write down a depth D formula, this is sort of maybe one of the first what I'll write down. And in particular, it's linear size, right? Any read once formula is linear size. It's a very nice regular structure. That's a Sipser function. So let's get some intuition as to why the Sipser function is so important for depth hierarchy theorems. So here's a challenge. I have a depth 3 Sipser, n to the 1/3, fan in, and or n or. And now it's nice and linear size. Now you point the gun to my head and you say, I want you to compute this in depth 2. Okay, so here's one thing I can do. I focus in on this n subgate. I rewrite an n of ors as an or of n's. Right, this is De Morgan. We can do that. But not very efficiently, right? How do you rewrite an n of ors and an or of n's? You take one from every bucket. So it's n to the 1/3 to the n to the 1/3. So it's roughly 2 to the n to the 1/3. Right, and you write this gate as an or of n's. Do this for every gate. And now you see that you have or of n's, and you can collapse the two ors, because an or of ors is or of ors. It's kind of, I don't know, this is one way to do it, but not very smart. And you can ask, whether there's a better way to do it, right? And what Hastad shows is that, essentially this is the best thing you can do. If you want to compute depth 3 Sipser with depth 2, just apply De Morgan, blow up the size. This is the best thing you can do. And same thing with depth 100, computing it with depth 99.
So you say essentially we really don't know at all anyway, and the lower bounds nearly match. So
nearly match. You do not get 2 to the n to the 1/3, right? You get 2 to the n to the omega 1 over d, right? So it's like you have lower bound of 2 to the n to the 1 over 100 maybe.
Okay, but let's say from a construction point of view, we don't know anything better than this.
Oh, strictly better? Like even just to save one gate?
Yeah. Well, not one gate, but let's say something in
I'm not sure. That's a good question. For depth 3, I do not know if I can prove a precise 2 to the n to the 1/3 lower bound.
No, but
no, I'm just saying upper bound.
Sorry?
The question is different. Can you save one gate?
I don't know. Yeah. The lower bound is definitely not delicate enough to capture that. You cannot. But maybe the upper bound is. Yeah. I wouldn't say that this is exactly optimal. Yeah. Okay. So yeah, that's a depth hierarchy theorem and some intuition as to why Sipser is the function to look at. Okay, so what have we shown? We have Hastad's theorem, which is nice. It says a parity not an AC0. In fact, depth d, what seems like large size, 2 to the n to the 1 over d, size circuits cannot compute parity. We have two extensions that feel somewhat different. One is that depth d circuits of that size cannot even approximate parity to 51%. The second one is that we don't consider parity, we consider a much simple function, and we get the same kind of lower bound against the same kind of circuits. So you can ask, and Hastad asked this, can I get the best of both worlds? Can I show that there is a function at depth d plus 1, such that if you force me to use depth d circuits and you allow me huge size, I cannot even approximate it? Right? That seems like a natural best of both worlds kind of extension. And our main result in this work is we confirm this conjecture of Hastad. Okay, so I'd like to tell you about this picture for the rest of the talk. Okay. So more precisely, and it's no surprise, we have the Sipser function. We show that for every depth d greater than 2, there's a function fd, the Sipser function, which is in depth d plus 1, AC0. But depth d circuits of size 2 to the n to the 1 over d, they have agreement half plus little of n. Okay, you cannot do 51%. And previous work, O'Donnell and Wimmer, in 2007, they proved the d equals 2 case. They proved, depth 3, Sipser, you cannot compute it in depth 2. You cannot approximate it in depth 2. And it was a starting point for us. We built on the techniques. And in particular, this is sort of the base case for us. So what we did is basically a depth reduction to the O'Donnell-Wimmer proof of the depth d equals 2 case. Okay, to answer a question that is probably on your minds, this correlation bound, right? A few slides ago, I said, parity is very, very hard for AC0. Your correlation is at most exponentially small, and here it seems like we're not doing much better. We're not doing as well. We only get 1 over poly n for d being constant. So you can ask, why not exponentially small? I have two reasons. One is just simply not possible for the Sipser function. The Sipser function is a monotone function, and it's a standard result that every Sipser function, every monotone function, has 1 over poly n correlation with a very simple circuit, either a dictator, an xi, or a constant. So you cannot hope to do this for the Sipser function. So this is not a very good excuse. You say, okay, find another function, a non-monotone function at depth d plus 1, for which you can prove exponential correlation bounds. But in fact, it's not possible for any function to begin with. If you force the function to be in depth d plus 1, which it has to because of the name of the game, it's a standard result that any depth d plus 1 circuit, it has 1 over poly n correlation with one of the depth d circuits that feed into the top gate. So there seems to be some fundamental difference between depth hierarchy theorems, correlation bounds, and parity. In particular, for the second reason, the second reason, you cannot hope for, half plus exponential in n to the 1 over d. So it's essentially optimal for constant, yeah. Okay, so that's our theorem. Let me touch on two applications of our result in two fairly different areas. One's in structural complexity, so forget everything about circuits. Let's talk about oracles relativization. So part of our job in complexity theory is we want to separate complexity classes. And we haven't been able to do so for many of them. And the famous example here is whether P is equal to NP. So we haven't been able to do it, so we can consider a twist of the question. Imagine a world where algorithms have free access to some magical function, call it A. Okay, you give A an input, and for free, in unit time, you get the answer. So think of A as 3 set, so you have this magical oracle that you give it a 3-set formula, and you snap your finger, and it tells you whether it's satisfiable or not. So in this world, you can ask whether P is equal to NP. It's a slightly different question, but it seems like a natural question. And the notation is, does P to the A equal NP to the A? Does P given an A oracle equal NP given an A oracle? So a priori, it's not clear that this is any easier than P versus NP, but actually for this, we have made a lot of progress even since the 70s. The paper introducing this notion of oracles, Baker, Gill, and Solovay, they noted that there exists some oracle for which you can separate P and NP. And this was improved a few years later qualitatively by Benedict Gill, who showed that, in fact, for almost every magical oracle A, P to the A is not equal to NP to the A. So we are still far from separating P versus NP, but at least in this, the oracle sense of the word, this is a pretty satisfactory solution. Right? Not only does there exist one oracle, for almost every oracle, they are distinct. Okay, that's great.
What is distribution? I mean, when you say almost all...
uniform distribution, say 99% or half minus little 1. Almost every function you can give, it's P is not equal to NP. And yet, that doesn't imply that P is not equal to NP in our world. So that's a little off topic, but as a caveat, this shouldn't be taken as evidence that P is not equal to NP for various reasons that we discovered later. Not we, but in the 80s, yeah. But that's a caveat. But it just independently is sort of an interesting question. Okay, so we have resolved P versus NP on these worlds. Let's move on to other questions. So here are two statements that we also believe are true. They both concern the so-called polynomial hierarchy. I'll explain what that means in a second. One is that PH, the polynomial hierarchy, is not equal to P space. The second is that PH is infinite. For this talk, it's actually not really important to know what either of these statements mean, or really what the PH is. These are two statements like P versus NP that we like to prove, but we cannot prove. And 2 is stronger than 1. And 2 implies P is not equal to NP. So 2 is very, very strong. So we are stuck on them, but we can ask, do these separations hold relative to one oracle? And if we can do that, we can ask, do they hold relative to almost all oracles?
1 is false, 2 is also false, right?
Yeah, okay.
Right, 2 implies 1,
yeah,
exactly.
yeah.
So 2 is a very strong statement. So let's see, we had success on the P versus NP question with respect to oracles, and we have much success here too. Yao and Hastad showed that the weaker statement that PH is not equal to P space holds for some oracle A. There exists a magical function such that PH is not equal to P space. This was improved by Tai and Babai, who showed that PH is not equal to P space for almost all oracles A. So the weaker question, we are very satisfied again. And Yao and Hastad also proved that in fact PH is infinite relative to some oracle A. And again, you can ask for, they conjecture that you have the strongest of all these statements. That in fact, the strongest statement is true for almost all oracles. That PH is infinite for almost all oracles A. So this would imply these results because PH being infinite for almost all oracles A implies that PH is not equals P space for almost all oracles A. And this version says it for just some oracle, and here we are saying it for almost all oracles. And in this work, we confirm this conjecture. And in fact, I'd like to touch on why this is a direct consequence of our circuit lower bounds. And if you may have guessed from the names of people who proved this, these relativization results are established using circuit lower bounds. So let me touch on this connection between circuits and relativization. Okay. So there is actually a tight connection between the class of circuits we're interested in, which is bounded depth circuits, which we think of as very limited models of computation. We cannot even compute parity. And the polynomial hierarchy, which is a very, very expressive tower of models of computation. And this correspondence was noted by first, Sachs, and Simpson. And roughly speaking, they differ by an exponential. And the connection is really, really very close. Depth 3 AC0 with an AND gate on top corresponds to pi 3. Depth 10 AC0 with an OR gate on top corresponds to sigma 10. Okay, there's really a one-to-one correspondence. In particular, I believe that this was the original motivation for proving circuit lower bounds. We wanted to use circuit lower bounds to prove lower bounds against the polynomial hierarchy. Okay, so let's take a look at the paper. It says, the title of the paper is Parity Circuits and the Polynomial Time Hierarchy. It says that a super polynomial lower bound is given for the size of circuits of fixed depth computing the parity function. Okay, and they say that connections are given to relativization of the polynomial time hierarchy. So this is a paper, and let's translate it. The first line basically says that parity is not an AC0. And the second says that, so they prove a super polynomial lower bound on the size of AC0 circuits computing parity. And they say that if you can improve it to super quasi-polynomial, then you have that pH is not equal to P space for some oracle A. Okay, it's quite easy. And so they didn't quite do this, but they noted that if you improve this separation to super quasi-polynomial, then you get this separation. And this was done by Yao and Hastad in '86, and not surprisingly, they proved this by proving the circuit result. They proved sufficiently strong lower bounds on the size of circuits computing parity. Okay. So in fact, we saw 2 slides ago, you have the circuit results and the 2 extensions. They correspond perfectly to a picture in the relativized world. Yao and Hastad, they proved that depth D circuits of large size cannot compute parity. And that corresponds exactly, and this was a motivation for them to show that pH is not equal to P space for some oracle A. You have 2 extensions, one of which says that you cannot even approximate it. That corresponds exactly to the strengthening of this theorem to say that the separation is true for almost all oracles A. You have another extension that says that depth D circuits cannot compute not just parity, but a super simple function at depth D plus 1 that corresponds exactly to the fact that pH is infinite relative to some oracle. And just like how you can ask for the best of both worlds in the circuit world, you can ask for the best of both worlds in the oracle world. And by confirming Hastad's conjecture, we confirm the conjecture that pH is infinite relative to almost all oracles. Okay, I'm not going to touch on this connection more, except to say that it's really a very, very close translation. It's really a mirror image. We didn't even prove that. It just follows by standard techniques. So, okay, that's application 1. It's sort of retro and old school. Let me switch gears to a different application now in the analysis of Boolean functions. Completely different. So forget all about oracles. So let me start with a very basic fact about circuits. Fix a function f. Consider the following very simple experiment. Draw a uniform random x, flip a coordinate. All right, it's so simple. And I want to know what's the probability that f of x is not equal to f of y. And I'm going to multiply by n. This is a matter of convention. Don't worry too much about it. But if you allow me to multiply by n, it brings it to a number between 0 and n. And it's known as the influence of f, on also like average sensitivity. And it makes sense. The name average sensitivity makes sense, right? It's average number of coordinates on which you're sensitive on. So given any function f, I can ask, what's its influence? Is it low? Is it close to 0? Or is it high? Is it close to n? It's just a measure of Boolean functions. And a famous theorem of Lineal, Mansour, and Nisan, sharpened by Boppana, says that if you give me some more information about f, you promise me that f is computable by a size s depth D circuit, then its influence is bounded by log s to the d minus 1. And again, the regime of parameters we should think of is s being poly n and d being constant, in which case LMN says that AC0 circuits have poly log n influence, which in the spectrum of 0 to n, we should think of as low. So it says that LMN says that small circuits of small depth have low influence. And it's a very important result. So let's look at the usual suspects. So this is the line of all possible influences. On the left, you have low influence functions. On the right, you have high influence functions. So let's start with high influence. Parity is the world's most influential function. As influence n. A random function has influence n over 2, so very influential. And majority is not hard to work out. The influence is roughly root n. For this talk, let's think of root n as high. Okay, so that's high influence functions. Let's look at low influence functions. You have the constant function, which is very boring. Its influence is 0. x1, which is also boring. Its influence is 1. These are not very interesting functions. And you have the tribes function, which is a DNF. Its influence is log n. Okay, so you have this spectrum with all the usual suspects in Boolean functions lying on it. And as you can see on the right is canonical functions, canonical examples of functions that do not lie in AC0. They are complex functions. And LMN says that this is not a coincidence. Again, for the range of parameters we should think of, size is poly n or even quasi-poly n. If the depth is constant, LMN says that you give me such a function, it lies to the left of poly log n. So in particular, LMN shows that majority and random function and parity are not in AC0. So it's a strong theorem about the stability of circuits. Okay, so LMN is great. a question that was asked by Benjamin, Kalai, and Schramm in a very famous paper about noise sensitivity and about influence, and it was repeated in a different form by O'Donnell, Kalai, and Hatami in the past few years, is whether the converse to LMN is true. Okay, what do I mean by that? LMN, vaguely speaking, says that small depth, small size circuits have low total influence. Is it true that low influence functions are basically circuits, basically small depth circuits? It's not hard to show that low influence functions, there are low influence functions that are not exactly a small depth circuit, but it was still possible that low influence functions are essentially small depth circuits and that you can well approximate it with a small depth circuit. So just to be slightly more precise, LMN says that if you give me the structure that you have poly size or even quasi-polynomial size and constant depth circuits, you lie to the left of polylog n. Okay, now you can ask, if you lie to the left of polylog n, do you have this structure? Are all polylog n influence functions well approximated by the same class of functions? If it's true, this would be a very, very nice characterization of low influence functions. But to spoil the suspense, we disprove it. We show that our main result gives a strong counterexample to this, which is unfortunate. And in particular, a question that came up during the times I gave this talk is, it would be nice to try to save this conjecture somehow. I'm very interested in the structure of polylog n influence functions. Yeah, and roughly speaking, as an aside for the experts, like log n is where Freedgaard's theorem breaks down. Like if your influence is below log n, Freedgaard's theorem gives you a very nice structure, but log n is where it doesn't give you any information. So I'm very, very interested in the structure of log n influence functions. And I was trying to prove this all summer, but ended up disproving it instead. So yeah, okay. So that's, again, it's a simple consequence of our main theorem. I'm not going to go into it. There's nothing there. It follows quite easily.
So the example again would be the
Sipsa function scaled up. Yeah, it's
Sipsa function.
Sipsa function of depth say square root log n. Okay, yes, some influence. And what does our main result show? It says that if you're any circuit of depth, not just constant, but square root log n minus 1 cannot even approximate it. So by adjusting parameters, choosing instead of square root log n maybe something else, you get a log n influence function that cannot be approximated even by super constant depth circuits. Okay. So yeah, again, our open problem is to rescue this somehow. Okay, so two applications. One is two fairly different areas. One is in structural complexity, which shows that pH is infinite relative to a random oracle. And second is to answer this BKS conjecture repeated by O'Donnell, Kalai, and Hatami, which is that unfortunately there's no approximate converse to LMN. Okay, so let me actually talk about the actual result. So for the rest of this talk, let me tell you about Hastad's techniques, the difficulties in applying them, and by that I mean applying them to get our result, which is an average case depth hierarchy theorem, and how our techniques overcome these difficulties. Okay, in particular, let me give a very, very high rough structure of Hastad's theorem, just in one slide and pictures. And I'll try to say why extension 1, the approximation version, follows easily. In fact, it's implicit in the proof. I'll tell you why extension 2 does not follow easily, and why Hastad had to do extra work to prove extension 2. And the way he proved extension 2, I'll explain why it breaks extension 1, why he loses average case hardness. And I hope to convey this tension between extension 1 and extension 2. If you wanted extension 1, you cannot get extension 2. And if you wanted extension 2, it was hard to get average case hardness. And how our techniques somehow are able to get both. Okay, but let's start with the very basic Hastad's theorem. In a picture, let's recap his proof. So one slide first about his main technique, which is that of random restrictions. It's a very simple concept. You take a Boolean function f, you apply a random restriction to it, you get a simpler Boolean function, f sub rho, where rho is your random restriction. I'll make this more precise in the next slide, but it was a very important concept introduced by Subodovskaya back in the 60s, but even till today is a really very indispensable tool in circuit complexity. Hastad's theorem uses it, and our theorem builds on it. So let me tell you about what a random restriction is. So a random restriction, you have some parameter p, think of it as small, say 0.1, or 1 over log n, and you generate, a string rho in 0, 1 star to the n. And how do you generate it? With probability p, independently, with probability p, you put down a star. Otherwise, you flip a coin and put down either zeros and ones. So the string you get out is roughly a p fraction of stars, and in the 1 minus p fraction is split half-half between ones and zeros. Okay, this is what a restriction is. What does it mean to hit a function with a restriction? So the restriction of a Boolean function f by this string rho is the function where you take in values for the stars, and for the non-stars, you fill in according to the template. Okay, so this is what it means to transform f into f sub rho. So as you can see, intuitively, this is, you do make the function simpler, right? There was an n variable function. Now it's a, pn variable function. So let's see what this does to functions. So this is what a random restriction is. So here's Hastad's theorem again as a cartoon. It says that parity, the red dot, doesn't live in the green circle. It lives at depth log n. So how do you prove such a statement? You hit the red dot with a random restriction, and you hit the green circle with a random restriction. And if you can argue that two different things happen to them, then clearly the red dot cannot live in the green circle. Right? So in more detail, you argue that parity, when you hit it with a random restriction, it remains complex. It basically becomes parity on fewer variables, but still very complex. You take AC0 and you hit it with a random restriction, you argue that it collapses to a really, really simple function, a small depth decision tree, which roughly speaking lies within here. It lies within like the bottom level circle. And then if you can argue these two, then to finish it off, you just argue that, simple functions cannot compute complex functions, and you're done, right? Okay, so of these three steps, one is essentially by definition of random restrictions and parity. It's not hard at all. 3 is a simple exercise that small depth decision trees cannot compute parity. The main technical work that Hastad had to do was the second step, to show that if you hit the green circle with a random restriction, it really, like the whole tower just collapses. Okay, so one slide about this main technical ingredient. It's his famous switching lemma. It says that you take any function in AC0, you hit it with a random restriction with carefully chosen p, depending on the structure, the size of the circuit. The depth of it decreases by at least 1. So to prove this theorem, you hit it d times. And you can argue that by hitting it, the overall restriction, it collapses to a very simple function. Okay, so there's one slide. We'll come back to this later, but that's really the main technical ingredient, and this is the technique that has seen lots of applications. Okay. So we just sort of sketched the proof of this parity not in AC0 result. In particular, for every depth d greater than 2, depth 100 circuits of large size cannot compute parity. Okay, and actually, I claim that we have implicitly also established extension 1. The proof implicitly gives average case hardness that not only can you not compute parity, your agreement is a tiny, tiny fraction. So let me tell you in one slide why this follows. It's a consequence of our random restriction. The key fact here is that our random restrictions hide a uniform random string. What do I mean by that? The phrase we have been using is they complete to the uniform distribution, which I guess is not very formal. But here's the formal meaning. You generate this random restriction row. All right, 0, 1s, and stars. And then now you fill in the stars with 0s and 1s uniformly at random. Consider this experiment. So at the end of it, you get a fully 0, 1 value string. The obvious but crucial fact that this gives average case hardness is that the resulting string is a uniform random string. And this is sort of why you have proved an average case hardness result. By hitting a function with this random restriction, you're implicitly feeding it a uniform random input. So this is why you get, and this is not hard to see at all, it's because when you're not a star, you're split between 0s and 1s. Okay, so I won't go into detail, but this is roughly speaking, the crucial fact behind why you get average case hardness. Okay, what have we done? We have sketched Hastad's proof of his basic theorem. We have shown why extension 1 is essentially implicit in the theorem. Let me tell you the more interesting thing as to why extension 2 is does not follow easily from Hastad's theorem, and why by proving extension 2 it broke extension 1. So here again is the statement of Hastad's theorem and its proof. It says that parity is not in AC0. And how you prove it, you show that when you hit parity with a random restriction, it remains complex. Whereas if you hit AC0 with a random restriction, you collapse to a simple function. And you just note that simple functions cannot compute parity. Okay, why can't it prove a depth hierarchy theorem? It's because for a depth hierarchy theorem, I want to separate, it's not delicate enough to separate depth d plus 1 and depth d. The lightning is too powerful. It destroys all of AC0. In particular, my hard function, say the Sipser function lies in here, and you destroy it, right? You try to do the proof, and you say, I hit my hard function with a random restriction. I hit depth d AC0 with random restriction. It shows that both of them collapse to small depth decision trees, and it doesn't give you the contradiction you want. But this was not trouble for Hastad. He was able to do it by designing new random restrictions, not yellow in color, but blue in color, designed specifically for the Sipser function to keep it complex. Okay, so in a picture, what he does is that he comes up with a new one, specifically with Sipser in mind, so that he very carefully keeps Sipser complex. He doesn't want to destroy it, and yet he still has to prove that anything of depth 1 less than Sipser still collapses to a decision tree. So he had to prove a new switching lemma for the blue random restrictions. And this blue random restriction was tailored very specifically for the Sipser function. So this is very nice. And particularly here, you see you're doing something much more delicate, right? Your contradiction comes in the fact that a decision tree cannot compute a depth 2 circuit. It really has to be very careful. Okay, so intuitively, just to say again, it's a much more delicate task, right? For parity in AC0, it's a nice result, but your hard function was really hard to begin with. So you just have to destroy AC0 and show that by destroying AC0, you do not destroy your hard function by too much. Whereas here, you're really trying to get very, very fine-grained information about the structure of circuits, right? You have to come up with something that destroys depth D circuits, but preserves your special function at depth D plus 1. So this was, but Hastad did it. So this is parity not in AC0, that's his depth hierarchy theorem. But he paid a price. The price comes in the fact that he only gets worst case depth hierarchy theorem. So recall the key fact about the usual random restrictions. It was independent across coordinates, and in particular, it completes to the uniform distribution. It's because you're implicitly hiding a uniform random string in the random restriction. Hastad's new restrictions that's carefully tailored for the Sipser function, your coordinates are not independent, they're carefully correlated to keep Sipser complex. Okay, and the distribution is only supported on an exponentially small subset of inputs, and hence you only prove worst case and not average case hardness. So just to summarize the difficulty that we faced when we tried to do this project. At a high level, there are 3 requirements for an average case depth hierarchy theorem. Hastad has 2 things, both of which achieve 2 but not 3. 1, you have to keep the target function, the hard function, complex. 2, your approximator, you have to destroy it. And 3, you have to do so in such a way that however you're hitting them, it completes to the uniform distribution. Okay, so Hastad's parity not in AC0 proof does 2, his famous switching lemma destroys AC0 circuits. It completes the uniform distribution just because it's so simple. You flip a coin independently for every coordinate. But his yellow lightning was too powerful. It was designed to destroy all of AC0. And particularly, it destroys the hard function that you're supposed not to destroy. Okay, so when faced with this, he said, no problem. I'm going to define a new random restriction that keeps my target function complex in depth D plus 1. I still prove that my switching lemma still holds, that it collapses, but the price he paid was that he did it so carefully and correlated the coordinates so carefully that it doesn't, it doesn't complete the uniform distribution. And in this work, we design a random projection that achieves all 3. And it's not hard to see that with random restrictions, you cannot achieve all 3. And the key idea here was, random projections. So let me, in my remaining time, tell you a bit about random projections and how do they relate to random restrictions. And if I have time, I'm not sure I do, but I'll sketch how projections achieve all 3. Okay, so again, our technique is random projections, which generalize this notion of random restrictions. So a restriction, just to recall, you take a Boolean function f over x1 to xn, you hit it with a random restriction, you get a simpler Boolean function over x1 to xn. A random projection, on the other hand, you take a Boolean function f over x1 to xn, you randomly project it, you get a new Boolean function over new formal variables y1 to ym. So this feels like a generalization because a restriction is just where your new formal variables are your old formal variables. Okay, let me be more precise. In a random restriction, every xi is either set to a constant, 0 or 1, or it survives. I have been denoting as star, but you can think of it as xi maps to xi. Right? That's what it means to survive. In a random projection, every xi is either set to constant like before, or you can map it to a brand new formal variable yj, where j doesn't have anything to do with xi. So you're basically changing the space of variables. And how do we exploit this? Very roughly speaking, in our proof, the new variables, the y variables, are much smaller than x variables. So we have a lot of collisions. Right? This is something that you cannot do in a restriction world. We map many different xi's to either 0, 1, or the same yj. And we map it in such a way depending on the structure of the Sipser formula. Okay. So again, projections, it's easy to see it's a generalization of restrictions because every xi, instead of mapping to yj, you enforce that it just maps to the same xi. Okay, so hopefully I can give you a sense of why this helps us. It'll be fast. And I'll do so, I will prove a weaker statement. I will show that, I'll show a separation between 3D and D. And you can see here you have to encounter the same kinds of problems because your hard function is in AC0.
Sorry, did you tell us the map or anything? No.
No, I'm going to come to that now. Yeah, hopefully I didn't skip. Okay, good. Yeah, exactly. I went back to the same place. Okay, so let me tell you about this projection and why. Okay, so it's designed specifically with Sipser in mind, right? So you have your depth 3D Sipser formula. It has, AND gates at the bottom. Let's look at the jth AND as some variables. Here's the projection. It's going to look a little weird. Every xi in the jth tribe, I set it either 1 or yj. So again, this is something you cannot do in restrictions, right? You just set all the, if you're not set to 1, you set it to the same variable yj. And again, recall that j is the name of the tribe. So in the jth plus 1, and you either set it to 1 or yj plus 1. Okay? And what's the distribution? Well, independently, we want it to be independent with probability 1/2, but we condition on not getting the all ones input. Roughly speaking, why do we want to do that? We do not want the AND gate to be satisfied. Right? If you put down the all ones input, the AND gates get satisfied. We want to keep Sipser complex. And here we see that we have not put down any zeros. So for an AND gate, if you do not put down any zeros, and you do not put down all ones, you keep it alive. In particular, it's always the AND of a non-empty subset of inputs, which is nice. But one thing you should be skeptical about is the claim that this completes to the uniform distribution, because I've only put down ones and no zeros. But roughly speaking, what's going to save me is the fact that I've grouped all this together. So by hitting it with very likely to be 0, it's going to be uniform. But anyway, so this is just one projection. As is standard in these depth hierarchy theorems, the over-random projection is just doing this over and over again. And if it's an OR, do it with the dual distribution with OR gates, with zeros and yj's. Okay, let's see why this helps us. There are 3 things. We need to show that this preserves Sipser, but that's essentially by definition, I hope. The second is that we still have to prove that AC0 circuits collapse to a simple function. And the third is that the restrictions complete to the uniform distribution. Okay, the first I claim is by design, and the 3 you should be skeptical about. So 1, why does it remain complex? Well, it's sort of designed with Sipser in mind. So the jth AND, you either map to 1 and yj, and you're never all ones. So it was always the AND of a non-empty subset of yj variables, and the AND of yj and yj and yj is just yj. So this is designed specifically so that the AND gate is never killed, and in particular, every AND gate just becomes a new formal variable yj. So what happens is you go from depth 3D Sipser over x variables to depth 3D minus 1 Sipser over y variables, with probability 1, right? So this is easy. Second one is the completion to uniform, right? Every coordinate is correlated in a way that you condition on not getting the all ones input. Okay, and the reaction should be that it does not look uniform at all, that you only have ones and yj's. But as you will see, the key here is that we are grouping the yj's together. So this is, it's an easy fact, but we were super happy when we found out about it, is that, if you put down a bunch of ones, you group the yj's, and then you hit the yj with something very biased towards 0, then the resulting string is uniform. And this is a calculation of the PMF, but what I really like about this is it allows me to generate a uniform random string in this 2-stage process, where I put down a bunch of ones, I group stars, and put down a bunch of zeros, and I group stars and I put down a bunch of ones. So what's really nice is that the usual way you generate a uniform random string is just go coordinate by coordinate and flip a coin. This allows me to just put down a lot of ones first, for my application, and then hit the remaining things as a whole. Okay, so informally, rho, which is very non-uniform, composed with this 2 to the bias product distribution, pops back to a uniform distribution. Okay, so that's nice. So I'm still missing one part, but I've already hopefully given you quite a good picture of what happens to the Sipser formula. You have depth 3D Sipser, there's AND gates at the bottom, accessing x variables, and your goal is to prove hardness of approximation with respect to uniform. You hit it with a random restriction. You go from depth 3D to depth 3D minus 1 very nicely, and your job, instead of proving hardness according to uniform distribution, you prove hardness according to the 2 to the w bias product distribution over your new variables yj. And again, what's each yj? Each of these collapses to a new variable, this collapses to a new variable, this collapses to a new variable. Okay, so what's nice is your target remains very structured, and your goal remains very structured. Your goal goes from product distribution to product distribution to product distribution. Okay, so the last step, the AC0 collapses to a simple function. I wouldn't go into detail, but as a last slide, as you would expect, we had to prove what Hastad proved, but for our random projections. So the key in Hastad's proof was a random restriction argument showing that any function in depth in AC0, it collapses to a simple function under random restrictions. You would hope that under one stage of what I described, just putting down ones and grouping things in the yj, you collapse by at least one, in which case we can apply it many, many times. We couldn't do that, at least for this random projection, but we could prove it if you allow me to hit it 3 times. So roughly speaking, this 3 is why I've only sketched a 3D versus D separation. I used 3 layers of my target to trade me 1 layer in my approximator. So if given 5D, surely I can get the contradiction. But with 3, I can prove that I get the collapse. So with that, I achieve all 3. So improving to D versus D minus 1, as you'll guess, we change it from red to orange, a significantly more delicate random projection to ensure that we get a collapse in depth even under just 1 random projection. Okay, and of course, once you change what your random projection is, you have to ensure that the 2 other properties still hold. That what was somewhat simple in my sketch, that is the fact that your target remains complex, which was really very neat in this example, but it gets more complicated, and the completion of uniform also. So a big part of the project was trying to juggle these 3 balls. We only could get 2 in the air for like 5 months. Then somehow one day we got all 3 in the air, and we were super happy. Yeah. Okay. Yeah. So just a summary, we prove an average case depth hierarchy theorem, which is for every D. Say D equals 100, that's a function that, if you allow me depth 101, I can compute it in linear size. But if you force me to use depth 100, if you allow me, what seems like huge size, my agreement is, less than 51%. And I gave 2 applications. One is that the pH is infinite relative to a random oracle, and a different application showing that, there's no approximate converse to this, famous and useful LMN theorem. And our main technique, which we're quite excited about, is this notion of random projections, which extends, this notion of random restrictions. And it'll be very nice to find further applications. So thank you.
Any additional questions?
So
Yeah.
how do you want to save the lineal Mansour Nisan?
That's a great question. I don't know.
So do you want to do something like, so what you show is essentially if it's polylog n for the sensitivity, it could still have high complexity, high large size.
Exactly.
So do you want to say maybe if it's not
It's
smaller than log n, then it cannot have large size?
Right, so at a very high level, like any structural information, I can prove about log n influence functions. And as I touched on, log n is a special number because anything lower than log n, we actually have quite strong, but not an easy theorem at all. It's a famous theorem of Friedgut, which says that your influence is k. You're essentially depending only on 2 to the k variables. So if you told me a function has influence 100, I can tell you, it's not a very interesting function. You essentially lie in dimension 2 to the 100. Right? If you told me influence is square root log n, you lie in dimension 2 to the square root log n. Where does it break down? If you tell Friedgut, your influence is log n, it tells you are, close to an n-hunter, which doesn't say much. So log n, I think, is a special number for me because I really like to understand the structure of log n influence functions. And this was very nice, right? BKS and O'Donnell and Kalai and Hatami, they said, maybe log n influence functions, you can depend on all coordinates, but maybe you're, a simple circuit. But it's not, you're approximated by a simple circuit. But it's not true. One way to rescue it is
log n or it's not? Because polylog, it could be log 10.
Well, that's an even more complex function. Right?
Yeah, so again, what is your result at when you said polylog n?
I see. I have a log n influence function. Yeah, I have a log n influence function such that if you allow me depth, not just constant, if you allow me depth square root log n, if you allow me size not just poly n, but 2 to the n to the square root log n, I cannot approximate it.
Okay, so even at log, it's not polylog n, it's at log n.
Right, exactly. I gave my counterexample at log n. Right. So a way to rescue it is to allow me broaden the class of circuits beyond just small depth circuits. So a conjecture would be that log n influence functions are well approximated by poly-size circuits, period. It'll be very hard to disprove because if you disprove that you have separated P from P/poly and P from, because in particular our function is clearly a poly-size circuit.
But wouldn't it be very surprising if this notion of sensitivity was a tight characterization for some notion of computational complexity? Yeah,
it'd be very nice, but could also be very surprising. Yeah, and in some sense, our results show that it was too much to hope for, right? It would have been really nice if, every log n influence function is basically just a circuit. If you're a circuit, small depth circuit, you're log n influence. If you're a log n influence, you're basically a. But yeah, exactly as you said, it's maybe on hindsight it was too bold, but yeah, it's not true. But still, one can hope for some sort of structure of log n influence functions. I'm not sure, yeah. A constant influence or square log n, we have very good structural information, right?
Thank you.
Thanks.